Assalamu alaikum, dear students. We're back with another video lesson. I hope you've been doing great. Today, we'll start solving some standardized test preparations, okay? So, if you remember in the previous lesson, of course, we did talk about rotational equilibrium, and then we talked about kinetic energy. We talked about the total, or in another word, we talked about mechanical energy as well. We said mechanical energy may be conserved, and of course, if it is conserved, that means the initial mechanical energy is equal to the final mechanical energy. And of course, we solved a lot of questions relating to that. Today, we'll start solving these questions, and then at the end of this, hopefully, if we have enough, if we're lucky enough to have some time, then of course we will solve some Zhyar questions as well. All right, so starting with this, we have a multiple choice question, of course. The multiple choice goes like this. Use the diagram below to answer questions 1 and 2. So for question 1 and 2, use this diagram. All right, so the first one says, 3 forces acting on the wheel above have equal magnitude. Remember, whenever it says equal magnitude, that means all these forces, F1 and F2 and F3, these all have the same magnitude or the same value, you can say. All right, and then it says which force will produce the biggest torque on the wheel. All right, so basically you're very familiar with this. We have 3 forces acting on the wheel trying to rotate the wheel, yeah? But you know that your first impression in this case, because F3 is not perpendicular or not at an angle to the axis of rotation, or F3 is parallel to the axis of rotation, so F3 produces no torque. Why? Because you can say F3 is acting on the axis of rotation, or you can say the extension of F3 is acting on the axis of rotation, so F3 produces no torque. All right, so what are we left with? F1 and F2, correct? And so take a look here. F1 is perpendicular, or you can say at right angle to the axis of rotation, you can say. And if that is the case, we know that because they are having the same magnitude, so F1, of course, will produce a larger torque in this case. So, of course, the answer is going to be F1 producing the greatest torque in here. All right, now we have the second question, which is related to the diagram, says what? If each force is 6 Newton. Now we have the value of each forces, which is 6 Newton. The angle between F1 and F2 is 60, and the radius of the wheel is 1 meter, don't forget. Okay, it is 1 meter. What is the resultant torque on the wheel? So remember, we don't want just the torque of one of the forces. We want the resultant of the forces, or the resultant torque on the wheel here. So remember, we have 3 forces. F3 is not in the equation. That is because F3 is acting on the axis of rotation, so no torque. So in this case here, remember this. Of course, we'll say the net torque here equals to what? Equals to, or you can say the sum of the net torques here equal to, of course, that would be torque 1 plus, let's say, torque 2, and then, of course, plus torque 3. But we said torque 3 will equal to 0 because it acts on the axis of rotation. So what about the net now again? Right? So we can say the net torque again, that is going to be torque 1, of course, F times d sine theta, right? Plus torque 2, once again, that is going to be F multiplied by d sine theta. All right, d sine theta. Let me write this one better. Perhaps these are different colors so you can see better. All right, so once again, torque 1 is going to be, we can say F1. Oh, no, let me go back. All right. Still not. All right, so once again, torque 1 is going to be F1 times d sine theta, right? And then plus for torque 2, of course, we're going to use F2 times d sine theta. And of course, or torque 3 is going to be 0 here. There is one thing that is very important, or what is the key idea in this question, of course. It tells you what. So let's write the first one here. It says F1, each one of the forces has a value of 6 Newton, so 6, right, times the distance, and the distance was 1 meter times sine theta. You can see here that the angle is 90, so sine 90 is 1 here, plus, that is for torque 1. Now, here is the major part why we're doing or solving this question here. Now, once again, for F2, which is, it has the same value, so that is going to be 6 Newton multiplied by the distance. Once again, the distance is also 1 meter multiplied by sine theta. Now, this is the idea of this question here. Remember, the question says what? The question says the angle between F1 and F2, this angle here is 60. But you know that when it comes to torque, we're going to use the angle between the force and, of course, the lever arm. So is this angle between the force and the lever arm for F2? Of course not, yeah? So, of course, or you can say the angle between the force and the extension of the lever arm, that is also true. All right, so if this angle is 60 degrees, what about this angle? Because this angle is the one that we need, not the other one. So, of course, this is 30, because you know that 60 and 30 will produce a right angle, which is 90 degrees in here. So again, that is the whole idea in this question. Otherwise, it's very similar to the previous ones that we have solved. This angle is given, but we're not going to use this. But of course, you need this angle so that you can determine this. Because 60 plus what angle equals to 90? Of course, that is 30, yeah? So once again, we need this angle right here, 30, not 60. Because in terms of torque, you're going to use the angle between the force and, of course, the lever arm, or you can say the extension of the lever arm, which in this case, that is 30 degrees here. So now, sine 30, right? And of course, you do know that sine 30 equal to half, yeah? Or 1 over 2, or you can say 0.5. So 6 times 1 times 1, that is 6, plus 6 times 1, that is 6 times sine 30, which is half, of course, is going to be what? Is going to be 3, yeah? So 6 plus 3, that is going to be 9, and of course, this is the net torque now, we can say, right? So in this case, we can say 9 Newton meter, and that is the answer, of course. So which one of the option would be? And one thing that I forgot, yeah? I did not mention the direction much because you can see that these forces are acting what? Acting counterclockwise. So of course, the net torque that you are getting, of course, it is positive. If it was clockwise, you would have gotten a negative value here. And of course, just to remind you here, we can use this as a clock or something. If this is 12, this is 3, 6, and 9, of course, the wheel is going to rotate like this. And of course, this is counterclockwise, or you can say anti-clockwise direction. So the correct option here is going to be option C. Well done. I hope you got it correct. All right, moving on to the next question here. And of course, this is the solution here. Moving to the third question. It says, if the same torque is applied to 2 pulleys here, right? And of course, this question came in 2012 as well. The same torque is applied to 2 pulleys of the same diameter to rotate with different angular speed, yeah? So one thing that we know, or you can say, what are the information here? We have 2 pulleys, yeah? The same torque applied. So we have 2 pulleys, and of course, the 2 pulleys have the same diameter, yeah? All right, and of course it says, but with different angular speed. All right, so we have the same diameter, but different angular speed. Can we say their moment of inertia are different? Well, possible, yeah, but we cannot tell for sure, yeah? What about their moment of inertia are equal? Again, it could be possible, but we cannot be very sure. But what about their rotational kinetic energy are different? That is the correct answer. Because as long as it tells you that there is a different angular speed, of course, it leads to a different rotational kinetic energy, yeah? Okay, that is because for rotational kinetic energy, we have, let's use this one, for kinetic energy of rotation, right? Rotation, of course, we have 1 over 2 moment of inertia multiplied by, let's erase the cross in here, omega squared, yeah? So having a different angular speed, of course, would lead to a difference in rotational kinetic energy. Their rotational kinetic energies are equal, of course not, because there's a difference in speed. All right, question 4 here says what? Which rotational quantity which rotational quantity is equivalent to mass in transition, yeah? So we've learned that mass, right, is, you can say the quantity that is used in translational motion, yeah? So what is the analog of mass in rotational motion? And of course, we'll use moment of inertia, yeah? So mass, that'll be in transition or in translational speed. Moment of inertia, I, would be in rotational motion. Don't forget, sometimes we use, let's say this, yeah? For example, let me give an example. Let's say in what? In kinetic energy. That is very simple for you to observe. So we'll use 1 over 2 mv squared, yeah? That is in translational speed. But in terms of rotational speed, we have something else, yeah? We'll use kinetic energy of rotation, for example. We'll use 1 over 2. What do we use instead of mass? We'll use I, yeah? So that is moment of inertia, all right? So, and of course, instead of speed, we use angular speed square. So the bottom line here, instead of mass, we have what? We have moment of inertia, and that is the correct answer here. All right, moving on. It says a force of 2 Newton applied tangentially to a disk of mass of 5 kilogram and a radius of 0.1 meter. What is the angular acceleration of the disk? Now, these questions are simple here, but in order for you to do it correctly, first of all, you got to know what you're given, yeah? And then, of course, a diagram would be perfect, right? If you understand the situation, you can draw this. So we have a disk, right? Remember, there's a force acting on the disk tangentially, of course. What is the value of this disk? You can do it here, or we can do it up this time. We've done a question similar to this before. So there is a disk. You can do a better shape though. So there is a force of, let's erase this a little bit. There is a force of what? There's a force of 2 Newton, right? Applies tangentially to a disk, and the mass of this disk is, what is it? 5 kilograms, okay? And then the radius of the disk is 0.1 meter. All right, so what is the angular acceleration of the disk? Now, in terms of this, remember, whenever you have force applying on a disk, of course, there's a net torque. This force tries to rotate the disk. That means there's a net torque. So we can say the net torque in here, right, equals to what? Equals to force, or was it? Yeah? Can we say moment of inertia, because there is mass and all that, yeah? And then multiplied by the angular acceleration? Let me erase the cross so nobody would complain, yeah? Whether this is cross or dot. Okay, so moment of inertia multiplied by the angular acceleration. So which one of this is unknown? Of course, it says find the angular acceleration. So how about we substitute numbers here? But do we have the net torque here? No. What else do we have instead? We have the force and the radius, yeah? So can I write force times the distance here? Excellent. And instead of moment of inertia, since I have a disk, and the moment of inertia of a disk is what? Is 1 over 2 times the mass times the radius, squared once again multiplied by the angular acceleration. Now substitute the numbers, do the math, you will get the answer. So once again, what is the force? 2 Newton multiplied by diameter, right? Or the distance here is going to be 1 or 0.1 meter. Okay, this is the radius, by the way, my bad, not the diameter, the radius. You can call the distance here as well. And then equals to 1 over 2 multiplied by the mass, which is 5 kilograms, not 0.5, multiplied by 5 kilograms multiplied by the radius squared, which is 0.1 squared, and then multiplied by the angular acceleration. And this is exactly what we want to find, right? So angular acceleration is what we're trying to find here. Now all you got to do is do the math. 2 times 0.1, that is 0.2 equals to half of 5, of course that is 2.5, and then multiplied by 0.1 squared, it becomes 0.01, yeah? And then you multiply the two, you'll get the answer. So let's use a calculator so that we do it right. So in this case, we can just do the whole thing all together, 0.2 divided by, and then we'll do, we'll calculate all this, and then we'll bring it under the 0.2, or divide both sides by this value, then you will get the answer. All right, so in this case, 0.2 divided by 0.5 multiplied by 5 multiplied by 0.1 squared. And of course, in this case, the answer will be what? Will be 8, yeah? But I think I'll have to do this side first, so you know what I've done here. So times 5 times 0.1 squared equals to 0.25 angular acceleration. So what is angular acceleration equal to? Divide both sides by 0.25, or you can just bring 0.25 here, and then you'll find the angular acceleration, which is 0.2 divided by 0.25, and of course the answer will be, yes, it will be 0.8, yeah? All right, let me just double check, because I got a different answer in the previous time. So 0.2 divided by 0.2, right, divided by what? Divided by 0.5 times 5 times 0.1 squared. Oh, I'm getting different answers here. What is wrong in here? Okay, clearly. All right, so let's do it again. 1 divided by 2. All right, that is 0.5 multiplied by 5 multiplied by, all right, multiplied by 0.1 squared. So the answer is going to be 0.025. 0.025. So now this 0.025 on this angular acceleration. So 0.2 divided by 0.025, the answer will be 8 in this case. So the angular acceleration here is going to be 8 because it is angular acceleration, that is radian per second squared. And that is, of course, the answer here. Okay, so do we have 8? Yes, and you can see here it is 8 radian per second squared. Moving on to the next question, take a look. There was a similar question that came in the 2023 WSAT questions, of course, but instead of asking for F1, they were asking for F2 here. Take a look at this question. It says, a man of weight 720 Newton stands on a light board. Light board, that means ignore the, let's say, the mass of, or the weight of the board, of length 2 meters that is fixed on 2 supports at its extremities, at the ends. If the distance between the point where the man stands on the first support is 0.5, what is the force exerted by the first support on the board? Now this is very interesting. Let's do this one. All right, and I hope you do know how to do this one as well. Let's get space where we can write on it, and then solve this together. All right, so take a look here. What do we have? We have a light board in here, and of course this light board is supported by 2 supports at the extremities, at the ends. Yeah? So you can call this one support 1, and this is support 2. There is a man of let's say 720 Newton, right, at a distance of 0.5, let's say far from the first support. Okay, so of course these supports are exerting a force upward on the board here. So there is, we can say, Fn1, or force of normal force, the first normal force, and this is going to be the second normal force by the support. Okay, so what is the question? It says, what is the force exerted by the first support on the board? Okay, and the length of this board is 2 meters. Okay, so now you do know that since the whole thing is balanced in this, so we can say the net torque in this case is going to be 0. In another way, if that is the case, we can say that means the torque, or the counterclockwise torque, must be equal to the what? To the clockwise torque. Yeah. All right, and that is what we have. So, but take a look. We're trying to find the force that is exerted by the first support. Yeah. If that is the case, then you'll have to make the second support as the axis of rotation. Because remember, how much force is applied by this, so you'll have to make this one the axis of rotation so that this one can move up, let's say, or the force can, let's say, push it upward so that it can balance the downward force which is exerted by the man in this case. All right, so now remember that the clockwise, so take a look, which one is clockwise, which one is counterclockwise? And of course, the force that is exerted by the support, once again, hold your pencil on the axis of rotation. So F1, it is going to be upward like this. So this is clockwise, yeah? This what? It's going to be like this. And of course, this is clockwise. What about the one exerted by the man? You could do this if you move this one downward. And of course, it will go like this. And this is, of course, counterclockwise. So the one that is counterclockwise is going to be the one by the man. So F, let's say, by the man, or Fg of the man, right, multiplied by the distance, right, is equal to, in this case, the force that is exerted by the first support multiplied by the distance. But be very careful here not to mix the distances, yeah? Remember, the force exerted by the man is 720 newtons, right, multiplied by the distance here. How far is the man from the axis of rotation? Remember this, the man is only 0.5 meter far from the end, yeah? The whole board is 2 meters. If we take away half a meter, right, so what is left in this case? And of course, this distance is going to be 1.5. So 1.5 up to this point, and here's another point, like another 0.5, we get a total of 2 meters, yeah? That is in terms of the distance. Okay, so we want the distance between the man to the axis of rotation. That is always the case, so don't forget this. So multiply by 1.5 meter equals to F1 support, or let's say the force exerted by the first support multiplied by the distance. Since this is at the edge or the extremities, we consider, or we'll use the whole distance, which is 2 meter in this case. All right, now both sides divide by 2, and then of course you will find F1, yeah? All right, so let's do this one. We'll say 720 times 1.5, right, equals to 1080, right, divided by 2. In this case, of course, we'll get, so we can say F1 or Fn1 will be 540 newtons, yeah? All right, so what if the question we're saying, what is the force? So basically that is the correct answer, but let me change the question here. What if the question wanted to wanted you to find the force exerted by the second support? That was the question that it came, yeah? In this case, we'll consider this to be the axis of rotation. And if this is the axis of rotation, what would happen in this case? Let me clear this side and tell you exactly what would happen. That's a different situation, don't forget. Okay, if the question were saying or asking, find the force exerted by the second support in the first place without mentioning the first. Excuse me. Sorry. So in this case, of course, we would do the same thing that we've done here. I'm not going to write it again, but in this case, of course, we'll say Fg of the man, of course, multiplied by the distance is equal to Fn2 this time, because the question we're asking for F2, and then multiply by the distance again. All right, so, but remember, this is the axis of rotation in this case. So 720 multiplied by, how far is the man from the axis of rotation? That is just 0.5, and then equals to Fn2 multiplied by the distance. How far is the second force? Of course, that is the whole length of the board, which is 2 meters again, yeah? So in this case, you'll just multiply this 2 and then divide by the 2, because we'll bring this to here, and then you'll find the force that exert on the board by the second support. So let's find this. 720 multiplied by 0.5, that is 360 divided by 2, and then of course we will get 180. So we'll say the force that is exerted by the second support is 180 newtons, yeah? Now there is another way you can find the force, like this one first, and then you can combine with this, you must get 720 newton. But remember, that is a long way ahead, we don't want this. You can just start with finding F2, and then using this you'll just find F2 here. But if the question were to, for example, find the force that exerted on both extremities or both supports, then of course we know that the upward force must equal to the downward force, yeah? So you will find one of the forces, and then you will equalize the two, for example. You would say 720, that is the downward force, yeah? 720, then the upward force must equal to this. So you will find one of the forces, for example, and then add with what force you will get 720, then you can easily find the second force. But here, luckily the question we're just asking for one of the forces, and of course the answer we found was 540, and that is the correct answer, yeah? Which one of the multiple choice? That is going to be option A here. All right, take a look at this one here. I like these sort of questions here, so pay attention. Not very difficult, I want to pay attention here. It says a disk of mass 0.5 kilogram and a radius of 0.1 rolls without slipping. Remember, we said without slipping. What does it mean? That means if there is an incline at the bottom, it would have both translational and rotational kinetic energy. Yeah? Even if it is rolling on a horizontal surface, that it would be the same in terms of kinetic energy. It would have both translational and rotational kinetic energy here. So what is the total kinetic energy of the disk at an instant when the instantaneous speed of the its center is 1 meter per second? All right, that is also an interesting question here. So let's solve this one as well. What does it say? It says basically find the total kinetic energy at an instant where it has a translational speed of 1 meter. Is it translational? Yes, of 1 meter per second. Now we want this. All right, so bear with me. Let's move this one down a little. We don't want the options here. All right, so it says a disk. So remember, whenever it says a disk, you'll have to think of moment of inertia of a disk. Yeah? Moment of inertia of a disk is going to be 1/2 times mass times the radius squared. Okay, keep this in mind because we're going to need this. So we have the radius, so we have the mass, which is 0.5 kilogram, right? And the radius of this is, what is the radius? 0.1 meter. Find what? Without slipping, of course, what is the total kinetic energy? So find total kinetic energy. All right, now we know that already. In order to find the total kinetic energy, because the object is rolling, so there's not just translational, right? It is both. We have translational and rotation as well. So in terms of total kinetic energy, right? Remember, total kinetic energy. Here we have kinetic energy of translation, right? Plus kinetic energy of what? Of rotation, all right? Rotation. But you already, again, you know that. So let's say kinetic energy again. I think I should write it smaller so we can have enough space. Kinetic energy of translation, it is 1/2 m v squared. V squared plus for rotational, it is 1/2. Instead of m, what do we use? We use moment of inertia multiplied by, instead of speed, we'll use angular speed squared, yeah? Okay, very good. Now, so once again, rotational kinetic energy equals to 1/2. You can substitute the numbers. The mass is 0.5 kilogram multiplied by the speed is 1 meter per second. So 1 squared, yeah, plus. Now, remember this, I'll use brackets here. So let's use this 1/2. Now, what is the moment of inertia of a disk? We said it that it is 1/2, right? Mass, of course, the mass is 0.5 times the radius squared. I'm not going to substitute the radius for now for one reason, yeah? Multiplied by, let's close the bracket for this one here, multiplied by the angular speed. What is the angular speed equal to? Angular speed equal to speed over the radius, yeah? Speed over the radius. But because it is squared here, so this two also becomes squared. So we can say speed squared over the radius squared. Now we can cancel out, this is squared. We can cancel out these radiuses together. So now this two will cancel out, correct? So what are we left with? We're left with speed squared. So let me add one more step to this. So we can say kinetic energy of rotation again. Total, I mean, not the rotation. The total equals to 1 over 2 times 0.5 times 1 squared. Let's write all this again, plus we can just go ahead with this 1 over 2 and 1 over 2, that is 1 over 4 times 0.5 times, and then of course the translational or speed squared, which is in this case is just 0. Is it? No, it's just 1, yeah? Not 0.1. 1 squared. Oops. All right, so 1 squared, yeah? 1 squared. Now all you have to do is just like rearrange and do the math, and that's it. So let's do this, yeah? 1 over 2, that is 0.5 multiplied by another 0.5 multiplied by 1 squared, yeah? And of course the answer for this is going to be 1 over 4 plus, and what about for this one? 1 over 4, that is basically 0.25 times 0.5 times 1 squared. We'll get 1.8, all right, plus 1.8 in here. Now all you have to just add these two numbers, yes? So 1 over 4 plus 1 over 8. And of course you will get a total of 0. So total kinetic energy is going to be 0.375 joules. And I hope you can see this, yeah? Let's move this one down. All right, so the answer to this is 0.375 joules because this is total kinetic energy. So remember the number, and let's see if we have it in the multiple choices, 0.375 joules. All right, now that was the answer to question 7 here. Now let's go and solve some short response questions here. All right, so let's answer this question. You didn't tell me your response. So of course the answer is yes, and I will tell you how or why exactly. So take a look here. Let's solve this together. So be with me. It says, can two spheres of different diameter have the same moment of inertia without, or let's say with different mass, of course, and different diameter? The answer is yes. When we say different spheres, of course, that means the moment of inertia of the first one must equal to the moment of inertia of, let's say, of the second one. So remember this. That is when we have, even though they have different diameter and different masses, yeah? But if that is the case, remember, we have two spheres, so of course there is a fraction. They could be solid sphere, they could be hollow sphere, it doesn't matter, right? But what we know is there will be mass, or mass 1 times radius 1 squared must equal to mass 2 times radius 2 squared in this case. And of course there is a fraction here as well. If we consider this to be solid spheres, for example, of course you know that is going to be 2 over 5 and 2 over 5 as well. There is an equal sign in between. So take a look here. Imagine what would happen, because they have different masses, right? So what will happen, or when will they have the same moment of inertia? We know that, remember this, moment of inertia equal to mass times the radius squared. But mass is inversely proportional with the radius squared, yeah? So, what happened if the radius of, or this radius was half of this radius, okay? But remember, so if the radius, or R2, was half of R1 in this case, we'll say mass, once again, 1 over half. If radius 2 is half of the other one, so we'll use 1 over half, 1 over 2, that is going to be half. But don't forget the radius is squared. So 1 squared, 2 squared is going to be 4. This 4 goes up. It becomes what? It becomes 4. That means if this radius here, if this radius is half, and of course the mass must be 4 times bigger in order to compensate for that, because this is squared, yes? So if that is the case, then of course we can say these two moments of inertia are equal. So we can say if this radius is half of this one, then of course the mass must be 4 times bigger than this, then we can have the same moment of inertia. Or another way, something very simple, you might not need even those parts, yeah? You do know that, for example, to get a constant in here, right, from both sides here, if this radius is half, 1 over 2 squared, you'll get 1 over 4, yeah? 1 over 4, so the mass has to be bigger by a factor of 4 so that it can cancel the effect of this. What if we had, instead of 1 over 4, what if the radius was smaller by 1/3, let's say? If it was 1/3, let's just say 1/3 squared, don't forget, you will get 1 over 9, yeah? So in this case, the mass has to be bigger by a factor of 9 so that we can compensate for that. But there is a different case, yeah? What if the radius was not half, the radius was twice as this one here? So let's say, what would happen if the radius was bigger than having a smaller radius than the other one? So let's clear this a little bit more. All right, so bear with me. Now let's reverse the situation. What do I mean by reversing the situation? If the radius of this was twice as this radius, it's twice, so 2 squared, of course, we'll get a total of 4, yeah? So, but if that is the case, if the radius is 4, then the mass has to be 1 over 4 so that these two can cancel each other out and we can get still the same moment of inertia. Now, let me erase a little bit more and so we can have more or something more obvious to see. Okay, so bear with me. We'll do two different things here. First of all, we know that moment of inertia equal to a factor, let's say it was for a solid sphere, and then mass times the radius squared. If the radius was twice, right, twice 2 squared, of course, 2 squared it would be what? It would be 4, yeah? So in this case, I'll just write 4 in here. Or maybe I'll write 4 right beside it, yeah? So 2 squared it will be 4. If the radius is 4, then the mass has to be what? It has to be 1 over 4 so that it can compensate for that, yeah? So that 4 and 4 cancel out, we get, like still the same moment of inertia or constant number in here, yeah? But what we were saying previously, what would happen if the radius was half? If the radius is half, for example, all right, let's erase these, okay? If the radius is half, what would happen? Yes, so 1 over, let's say the radius is half. Let's get this back. All right, if the radius is half, 1 over 2, and square this, of course, you will get what? You will get 1 over 4. So if the radius was 1 over 4, the mass has to be 4 times bigger so that they can cancel each other out. But remember this, yeah? These numbers are just not 1 over 2, half, or triple, or twice, or whatever. Yeah? You can add any number to this bracket and then square it. Then, of course, the mass either has to be by the same factor, whether bigger or smaller, so that we can get the same moment of inertia. So what if the radius was 1/3, 1 over 3? Then, of course, we'll get 1 over 9, yeah? And then the mass has to be bigger by a factor of 9, yeah? What if it was 1 over 4? 1 over 4 squared, you'll get 1 over 16, let's say. Then the mass has to be bigger by a factor of 16. If you do the reverse here, if, let's say, the radius was bigger by a factor of 2, and 2 squared, of course, you know that equals to 4, then in this case, the mass has to be smaller by a factor of 1 over 4. If the radius was, let's say, 3 times bigger, 3 squared, of course, we'll get 9. So the mass has to be smaller by a factor of 1 over 9. And this is how we can get 2 spheres of different masses and different diameter, yet the same moment of inertia. All right, moving on to the next question. It says, in which case would an angular momentum be conserved? Now, that is very obvious. We said there is one case where the angular momentum can be conserved, and that is if the net torque acting on the object is 0. Whenever the net torque acting on the object is 0, then that is where the angular momentum is conserved or can be conserved. Does the conservation of angular momentum lead to the conservation of kinetic energy? Absolutely not, because we said some work might change to rotational kinetic energy without any external torque. And then if that is the case, then of course the rotational kinetic energy will not be conserved. Remember when the hands of the ice skater were, let's say, closer to his body, the rotational kinetic energy were higher, right? And then once they were extending their arms, the rotational kinetic energy were decreasing without changing, without any net torque acting on the object. So in these cases, the rotational kinetic energy were not conserved. And of course, this question is not included because it is cancelled. Now, of course, this is the summary. I would recommend you to go through the summary and go through the important parts here. Now, we have some past, let's say, paper questions or past international or national questions, or as it is common, we can just call the past WSATic questions or exam questions. Yeah? I'm not going to solve all of them, but I would recommend you try all of them whenever you're free. All right, so the first, I'll go through some of the questions here. In which of the following situations should the object be treated as a point mass? Here we said, whenever the center of the object, if it is rotating or spinning, then the object is considered as an extended object. If the center of the object is not rotating, then we can consider the object to be as a point mass. So Earth rotating about its axis, there's rotation, so extended. A wheel rotating, rotation extended. A ball rolling, extended. And a ball dropped from the roof. If a ball is dropped from a roof, that means it just free fall without any rotation, without the center of the ball being spinning or rotating. So of course we can consider D, a ball falling or dropped from the roof, as a point mass. All right, this is very similar to the first one. Which rotational quantity is equivalent to mass in what? In translational. Of course, moment of inertia would be the analog to that, okay? So moment of inertia, that would be for the mass. If the same torque is applied to two pulleys of the same diameter to rotate with different angular speed, whenever we have their angular, or the angular speed is different, if the angular speed is different, can we say their rotational kinetic energy is the same? No. So their rotational kinetic energy will be different. And a solid 240 ball with the radius of this roll 6 meters down a ramp, that is inclined at 37 with a horizontal. If the ball starts from rest at the top of the ramp, what is the angular speed of the ball at the bottom of the ramp? So remember this. We said, first of all, we have a solid ball, and rolls down a 6 meter down the ramp. Yeah, so this is not the height, this is the length of the ramp, or delta x, and we have 37. Let me solve this one for you real quick. And all right, let's move this down a little bit. So there is only one thing that I want you to know is, in here we're going to use sine theta to find the height. Once you find that, you'll use the usual equation, and that's it. Yeah. So here's the ramp, okay, and this is the length of the ramp, or delta x, which is 6 meters. All right, and then this angle is 37 degrees, and this height is unknown here. We want what? We want the rotational. We want the angular speed. What is the angular speed? Remember, we don't want the translational. We want the angular. So first you need to find the translational speed of this, and then of course you will be able to find the angular. But before that, we have sine theta equal to what? Equal to opposite over hypotenuse, yeah? So once again, sine 37 equals to opposite is, that would be the height here. What is the opposite of this angle? That is the height. And then hypotenuse would be delta x, which in this case is just 6. Now, in order to find the height equal to 6 times sine 37 degrees, let's find the answer to this one here. Okay, so 6 times sine 37, we'll get 3.61. So the height is 3.61 meter. That is the height. Let's not circle the whole thing, yeah? So the height is 3.61. Now, if we know the height, we can find the translational speed. How about we use a different color here? So let's use black. All right, so in this case, translational speed equal to the, remember, fraction. What was the fraction? We said a solid ball, solid sphere, yeah? And the moment of inertia for a solid sphere is 2/5 mr². 2 times the denominator, numerator plus denominator. That's 2 plus 5, 7 times 9.81. Let me write the equation first. Times g times the height, yeah? And of course we can say translational speed again, 10 over 7 times 9.81 times the height, which we found, which was 3.61, yeah? So do the calculation. 10 over 5 or 7 multiplied by 9.81 multiplied by 3.61, we get 7.11. That is the translational speed, 7.11. But remember, we want the angular speed, yeah? And you do know that angular speed here, angular speed equal to translational speed divided by the radius, correct? So in this case, we can say 7.11 divided by, what is the radius here? That is 0.20, yeah? So 7.11 divided by 0.20, and of course the answer is 35.55, or you can say by rounding that is going to be 36 radian per second, and that is the angular speed at the bottom of the equation. And of course the answer must be C in this case. Okay, now next it says kilogram meter squared over second is the measuring unit of which of the following physical quantity? Is it the mass? Is it the angular speed? No, angular speed is just radian per second. Is it the torque, or is it the angular momentum? For torque it is Newton meter, so it is the angular momentum. And how do we know? Or you could just say angular momentum L equal to moment of inertia times angular speed. Moment of inertia, that is kilogram meter squared, yeah? As for angular speed, it is radian per second, but we just use 1 over second because we don't use radian, or radian is not the SI unit here. So we can just say kilogram meter squared over second, and that is the unit of angular momentum. All right. All right. Question 7 says, a rigid ball starts rolling from an inclined surface without slipping. Then, right, if it is rolling without slipping, that means there is rolling here. So which one of these options will be correct? It has only kinetic energy, or it has rotational and linear. It has only linear, it has neither, and of course it has both rotational and linear kinetic energy. Because it is a rigid, it starts rolling from an inclined surface without slipping. So as long as there's rolling, moving, it has both types of kinetic energy. A point at which a mass is considered to be concentrated, that is center of mass, you already know it. The product of rotating objects' moment of inertia and the angular speed about the same axis, you do know this, yeah? This is the angular momentum. Moment of inertia multiplied by the angular speed, yeah? That is angular momentum. And you do know this. We've solved questions like this. This is very easy. I believe a bonus question. The perpendicular distance from the axis of rotation, that is the lever arm, for an object to be completely in equilibrium, I would like to make a pause on this. For an object to be completely in equilibrium, there must be no net force, and also there must be no net torque. If these two met, then of course we can say the object is in complete equilibrium. So which one? Only net force, only net torque, net force and net torque must be 0. So the correct option here is C. Which of the following quantities measures the ability of a force to rotate an object down? That is, of course, that is the torque. The moment of inertia of an object generally depends. This question is important. Moment of inertia generally depends on what? Depends on all these factors. Why? Because, let's say the moment of inertia of an object, I equals to a number times the mass times the radius squared. This number here depends on the shape, yeah? And of course here the mass, and here's the radius as well. So depends on the mass, yes. Depends on the object's shape, yes. Depends on the distribution of the mass around the axis of rotation, and of course that is the r as well, you can say, yeah? So, or another way, yeah, that'll be the radius, you can say, yeah? So of course all this would determine the moment of inertia of the object, so we can say the correct option here is D. All right, a solid ball starts from rest at a height of this. The translational speed of the ball when it leaves the incline is what? Once again, Remember the moment of inertia of a solid ball, right? Of a solid ball again, it is 2/5 I, or you can say m times or mass times the radius squared. Yeah. So for the translational speed, right? We said the square root of what? Of 2 times the denominator, numerator plus denominator, and g and h. Yeah. Okay. So 2 times denominator, 2 times 5, that is going to be 10, right? So let's write this one. It's going to be 10 over numerator plus denominator, that is 2 plus 7, 5, that is 7, GH, yeah? So this is going to be the correct one. So which one is this? That is option A here. Okay, moving on. Moment of inertia of a solid sphere around diameter can be found by this. These are easy. The SI unit for torque, easy. Which of the following equation is correct for the rotational kinetic energy? Again, very easy, you know it. An object's moment of inertia, is this, the speed is this. What is the angular momentum? Angular momentum, moment of inertia multiplied by the angular speed. These are easy. Okay, let's see. Which one of these questions are interesting so we can do? This is also very easy. A force of 2 Newton applied tangentially. We've solved questions like this. Take a look at question 25. The approximate location of the center of mass of which the object is in the middle along, along the inside, of course. That is the banana, yeah? Okay, 25 and 5. Conditions of equilibrium are not applied here. A bicycle wheel rotating along a level highway at a constant speed, a bicycle parked against a curb, and then the tire of on a parking automobile that is still moving. That would be the correct answer because the conditions of the equilibrium are not applied here, you can say. Which of the following statement is correct for an object rotating with a constant angular speed? If it is rotation, by the way, here says rotating and constant angular speed. So of course we can say the net torque acting on the object equal to 0. The net torque acting, the object is not at equilibrium, there's no equilibrium. We can say the net torque on the object is not equal to 0. No, that is option A. The net torque acting on an object is equal to 0. That is why the object is rotating at a constant angular speed. And then the rest are easy, I believe. Let's see if there is anything else that is interesting. Angular motion with the analog of linear. By the way, in angular motion, what is the analog of linear momentum? So we have linear and angular momentum, yeah? So if it is linear, the analog in rotational motion would be the angular momentum. Linear momentum, angular momentum, easy. This one is also, take a look. If the torque required, we've solved a question like this, I believe, as well. Let me give you an idea for this. All right, remember the torque, you already know that. The torque that we have, all right, the torque, what is the torque equal to? All right, we know that the torque equals to force times distance sine theta, yeah? You're given the torque in here, right? It says find the force, yeah? What is the minimum force? So this force is unknown here, right? You're given the distance, you're given the sine theta, so just plug in the numbers, you'll be able to find the minimum force in here. Okay, what else do we have? We've solved questions like this. I would recommend you to go back to where, like the section where we solved questions related to seesaws and how to balance. That is the rotational equilibrium. The moment of inertia for a regular object and all that. These are easy. Solid ball, easy. Let me go through this one more time. If a solid ball rolls down from a top of incline, a plane of inclined plane of height 2 meters to the bottom without slipping, and at second hand, the ball falls down freely from 2. By neglecting the resistance, the final speed of the ball center depends on the mass when it rolls down. B says it is equal in both cases. Not equal. It will be greater when it rolls down. No, it will be greater when it falls down. Why? Because we said it is greater when it falls down. That is because when it rolls, part of the total energy will change to rolling, and of course we'll end up with less, let's say, energy or kinetic energy at the bottom compared to if it is just falling from the same height. Okay, and you can see there are more questions to this. Force of 20 Newton perpendicular to this on a body produce a torque of this much around this. What is the distance? That is very easy. Torque equal to force times distance, and then you can find the distance by plugging in the numbers. We solve questions related to this. This is very important, yeah? All right, and okay, remember this. We had some keys to answer questions like this for rotational to total kinetic energy, yeah? Let me remind you about this. If we have, like for kinetic energy of rotation, we say whatever the moment of inertia for the object is, always use this, yeah? We'll set numerator over numerator plus denominator, yeah? And then of course you will find the ratio of rotational to total. So what is the shape in here? It tells you, it is this one here, yeah? So if we do this one, numerator is 1, yes? So that is 1. For the bottom is going to be numerator plus denominator. So 1 plus 2 is going to be 3. Which one is 1 over 3? That is B. And of course that is the correct option here. All right. So I think we're almost at the end now. Identify which condition of equilibrium hold for a bicycle wheel rolling down. These are easy. And then let's take a look at the last question here, which is 52. Right? I think it's worth solving this. It says, at a circus performance, a juggler is throwing 2 spinning clubs. One of the club is heavier than the other. Which of the following statement is true? The smaller club is likely to have a larger moment of inertia, right? Let's take a look at the other options. It says the ends of the club will trace out a parabolas as the club is thrown. C says the center of the mass of the club will trace out a parabola as the club is thrown, and both B and A and B are correct. And of course, this is the correct option here would be C, but let me tell you why it is C. Right? So if these are, let's say, the 2 clubs, this is one of them. This is not perfectly. Let's say this is one of them, right? And these are not very good in drawing, so don't complain. We have 2, yeah. One of them is heavier. It could be the same size though. So let's clean up this. Right, 2 spinning clubs. This is one. This is the other one, but of course one of them is heavier than the other one. So the smaller club is likely to have a larger moment of inertia because they could have different shapes, or the shapes could be not 100% the same. So we cannot say A is true, yeah? But as it spinning in the air, what will happen? Let's say this is what happens here. We know that the 2 ends of this would spin about or rotate about the center of mass of these clubs, yeah? But one thing for sure that is always that the center of the club will always trace a parabola, yeah? It is always behaves like a point mass that is moving on a parabola path, you can say, and this is why option C would be the correct answer. And I would recommend you practicing more. As you can see here, you can see all the answers. You try to solve these questions, and then you can compare your answer with the answers that I have in here, and I wish you best of luck. So that is the end for today's video lesson. Until another video lesson, keep practicing and stay safe. Assalamu alaikum wa rahmatullah.